All right, welcome everyone to our Grasp on Robotics series. Starting just a little bit late. My name is Mark Yim. I'm the faculty host for today. Quick reminder, previously recorded talks can be found on our YouTube channel and our website. And if you're joined by Zoom, please submit your questions via the Q&A button. They'll be addressed at the end. We have two of our panelists, our PhD students, Shivanji Misra and Akshay Panyam. They are working on a NASA Luster project, so they're very excited to see our speaker today, Terry Fong. Dr. Terry Fong is the chief roboticist at NASA Ames Research Center and the deputy rover manager for Viper, which we'll hear more about. It's a very exciting project. Terry previously led a bunch of projects, and one of the more interesting ones is also the Astro B project that actually flew on the International Space Station in 2019. Terry has published more than 175 papers in space and field robotics, human robotic interaction, and virtual reality interfaces, as well as planetary mapping. Terry received his BS and MS from MIT and his PhD from CMU. Please welcome Terry Fong.
Thank you very much, Mark. Good morning, everybody. I will admit right now, this is the first time I've ever been on campus here at Penn, and I won't say the other Pennsylvania University or the one that I'm an alumni from Western Pennsylvania, but it's a great pleasure to be here. I'm going to spend today talking about the Viper lunar rover mission. So first off, how many people have ever heard of Viper? Actually, wow, that's more than half people. For the other half who are not familiar with it, this is a lunar rover mission, so a space robotics mission that's been under development for the past several years at NASA. The mission was originally intended to fly at the end of this year, but last July, for a variety of reasons having to do with budget and in particular, the budget associated with getting it from the rover from Houston, where it currently is, to the moon, NASA decided to hit pause on the mission. At that time, it was actually canceled, but then it was turned into a process that NASA is going through for the very first time of trying to develop a public-private partnership, that is the federal government partnering with industry to fly NASA's rover to the moon. And that's actually an active, ongoing thing right now. There was a call for proposals, the first step of which closed just this past Monday. So I do expect to see Viper on the moon. I just can't tell you exactly when. But let's dive right on in here. And the first thing I want to tell you about is not anything about the rover itself, which we're going to spend a lot of time talking about today. But hello, let's try this. OK, but we'll start off by talking about the moon. Now, the moon, of course, is something that you can see every night. There's a clear sky. It's not yet full. In the next week or so, I think it will get to be full. When you look up there, one of the things that you should think about is the fact that up until about two decades ago, everybody thought that the moon was a barren, bone-dry place. Actually, pretty uninteresting because it was just, a bunch of rocks and lunar soil. But the thinking has really changed ever since then. In particular, there have been a number of lunar missions, orbital missions, and then a mission that NASA Ames flew several years ago called L-Cross, which actually impacted the lunar surface. And the thinking now is that actually the moon is not bone dry. That in fact, the moon is a really fascinating, wonderfully rich place that holds lunar water, or in particular, different types of different species of hydrogen, one of which could be subsurface water ice. But in fact, the moon is now well known because of these various missions and analysis from the data from these missions to host the three forms of water in the solar system. Internal, that is, water that may have existed since the formation of the moon, or that arises from the interior materials in the moon. Water that is delivered by asteroids or comets. This is the most common way that we've thought about how water can get to the moon. That is the impact of water-bearing things such as asteroids and comets. And the third, in situ, things that are emplaced by the solar wind interaction with the lunar surface. Now, what's interesting about this, of course, is that water by itself is an interesting scientific phenomenon, but from the human exploration side or the space exploration side, it's actually even more important than that. One of the important things is, of course, that if we have hydrogen, And then we can get oxygen, which is well known to be possible by basically processing lunar soils and recovering oxygen. Of course, now you have the ingredients for water, and more importantly, you have the ingredients to make fuel. And that would actually change the entire point of why you would care about the moon. So rather than just being someplace to go as a destination, it could actually be the starting point for expanding human presence in the solar system, expanding our ability to explore from the moon, and not to bring everything from Earth, which is incredibly difficult because Earth has so much gravity and it's so expensive to launch things from Earth into space and going beyond, say, the Earth-Moon system. So then, given that the moon has water, the question, of course, is where is it? What concentration is the water in? What form is it in? Is it something that can be easily recovered, and can we make use of that in some way? Now, there are a lot of reasons why water is not stable on many parts of the moon, having to do with the exposure, especially to sunlight, which will tend to sublimate any sort of water that's on the surface or in the near subsurface, especially if the temperatures increase over time. And so one of the things that we have done at NASA is try to characterize the moon in terms of different areas where ice can be stable, that is stable over long periods of time. Certainly, there are areas where the ice can be stable because it's really deep, that is buried beneath this wonderful insulating layer of lunar soils. There may also be areas where it can be stable in the near subsurface or even at the surface because areas are in darkness, either most of the time or all of the time. And in fact, there are areas that are very interesting called permanently shadowed regions, or PSRs. I'll apologize if I speak in acronyms, because if you go work at NASA, the first thing you're told is you have to stop using full sentences, you have to speak in acronyms. So PSRs, permanently shadowed regions, are areas that never see sunlight. They are in permanent darkness. This occurs because of geometry in principle, especially if you get towards the higher latitude regions, towards the poles. There are areas which are very large craters. Shackleton crater, as an example, near the lunar South Pole, is like 20-kilometer diameter crater in permanent shadow. But there are also places where you have smaller ones, even as small as, say a few centimeters across, just because of the orientation of, say, a crater and its surrounding environment. But because these locations exist, that means they make good targets for investigation. Can we go map these out and see, given that we know the conditions would sustain subsurface water ice or other subsurface species of hydrogen, can we go access these and make measurements to understand, is there in fact hydrogen? And again, what state, what concentration, what distribution, laterally and vertically?
The future of human space exploration is being driven by what we can discover and accomplish on the moon. And with NASA's confirmation of ice existing at the lunar South Pole, the critical task of finding and mapping where water exists, what form it is in, and where it came from can now begin. Leading us on that journey will be NASA's first mobile robotic mission on the moon, known as Viper, the Volatiles Investigating Polar Exploration Rover. It will be delivered to the Nobile region of the South Pole as part of NASA's Commercial Lunar Payload Services Initiative. This region sits just outside the western rim of Nobile crater and covers an area of 36 square miles. As the first ever resource mapping mission on the surface of another celestial body, Viper will roam the surface equipped with 3 science instruments and a drill to detect and analyze various lunar soil environments at a range of depths and temperatures. The rover will venture into permanently shadowed craters, some of the coldest spots in the solar system, where ice reserves have been preserved for billions of years. NASA had 4 critical parameters when choosing a landing site for Viper: available sunlight, Earth visibility for communications from the moon to the Earth, data showing the potential presence of water and other resources, and terrain that is well suited for Viper to navigate. The area to the west of Nobile crater met these conditions. Once on the surface, Viper's mission will last 100 days and cover between 10 to 15 miles. And while a baseline traverse route through the Nobile region has been identified for the rover, the scientific discoveries Viper makes along the way will actually influence where the mission team sends it next. So its planned route will most likely change. During its travels, Viper will visit at least 6 locations where data suggests ice could be found. By helping determine the locations of where water and other resources exist, Viper's findings will help pave the way for future landing sites under NASA's Artemis program. The prospects of achieving a long-term human presence on our moon never looked so bright.
So I think the video does a nice job of giving you a very high-level overview about the planned Viper mission. What we're going to do over the next few minutes is talk a little bit more about the mission itself and then dive into the details of how we've actually designed the rover system. So the hardware, the software, and mission operations. But to begin, this mission, as the video was just saying, targets an area near the lunar South Pole, the western side of the Nobile crater region. It was designed to be about a 100-day-long mission. That's partially driven by the science measurements that we were interested in accomplishing, plus what's possible with a purely solar-powered, battery-backed-up rover, dealing with things such as the continually changing lunar day-night cycle, which at most places on the moon are 2 weeks sunlight, 2 weeks darkness. But there's some interesting things about those lunar South Pole, especially in high elevations, that allow you to do clever things like only have to survive night for a few days if you get to the right location at the right time. The overall science objectives, of course, for this mission is to characterize the distribution and the physical state of volatiles, in particular water ice. And to do that, we use, as the video was saying, 3 spectrometers and a rotary percussive 1-meter drill to access the near subsurface. The mission is really fascinating from a design point of view. If you're a system engineer, anybody who likes really complex, difficult design, this is exactly the kind of mission that you live for, because there are a lot of interesting things about the lunar environment. This is, for example, the first really dynamic environment, surface environment that NASA's ever had to design to. The fact that we have moving, light and shadow all the time really complicates factors for a solar-powered rover. It's a real-time interactive mission because we're close to Earth, and so we don't have to wait for data. We only have to wait a few seconds for data to be downlinked. It's a prospecting mission where we're always trying to move and take measurements while moving, and because of that, science can be fundamentally interactive. As I said, it's a really sort of unique opportunity to try to inform not only scientific understanding, but to actually inform the future of what do we do with resources from the moon. And to that end, Viper really sits at the sort of like middle point between what's been done before by government agencies. In particular, NASA has spent a number of missions that have studied the moon from orbit. In fact, the LRO, the Lunar Reconnaissance Orbiter, still is functioning today. It was originally designed primarily as a lunar mapping mission, so it has high-resolution cameras that continuously fly over the moon and take pictures of the lunar surface in stereo that we can use to build 3D terrain models. LRO also has a laser altimeter that provides additional 3D ranging measurements, as well as other missions that have carried spectrometers from orbit. But these are all sort of the starting point for any sort of prospecting type mission, because of course, having orbital data is insufficient. You need to actually ground truth that. And that was the whole point behind the inception of Viper, to create a mission that could acquire ground truth surface level measurements. And once you have those things, then of course you can move on to the active phase of, at least from a resource point of view, thinking of, now that we understand what's there, how do we take advantage of that? And there's been a tremendous, I think, focus from US and international industry on answering that question. But of course, industry is not ready to jump forward and say, oh yes, we're going to go build the greatest gas station in the sky until they know what's there. And right now, that's been the primary focus for, as I said, for example, space agencies like NASA and other international space agencies. Viper is also at this interesting intersection between science, exploration, and commerce. Obviously, from a scientific point of view, we do want to understand, where is the water, and then from that, understand, why is it there? How did it get to be there? How is it actually sustained over time? From an exploration point of view, as I said, we're interested in understanding, can we make use of these resources? Would this allow us to be able to use the moon as a staging point for exploration on the surface, near areas, for example, where there may be these subsurface water resources, or to go beyond the moon. And then from a commercial standpoint, of course, I think it's fascinating, the idea that we might actually use the moon not just as scientific curiosity, but as the next place where we want to expand our influence as humans. And of course, from a commercial standpoint, that means, well, is there a business to be had of using the moon? I will say that when we started Viper, one of the things that we were given as direction was to think of Viper as not your typical NASA mission. Now, of course, this was at the end of 2018. We actively started working on Viper in 2019. It was designed to be a mission that would be designed rapidly at significantly lower cost than prior planetary rover missions. You look at Perseverance on Mars, that was about a $2.4 billion mission. We were trying to design Viper to be like a $200 million class mission, so about 1/10 the cost of a Mars mission. To do this, one of the things we wanted to do was take advantage of off-the-shelf commercial components, commercial software, and open source software to the greatest extent possible. And we wanted to try to take advantage of the fact that it was going to the moon to do things which you just frankly could not do on Mars. And I'll talk about those things in a minute. Now, of course, that was back in 2019. We all know what happened in March of 2020, a little thing called the pandemic. And I will tell you, trying to design a flight mission in the middle of a pandemic was a huge challenge. Not just because NASA had never tried to figure out how do you do system engineering of a flight vehicle remotely, from home, but also the long-term effects of what the pandemic did to all the commercial components that we were saying, oh yeah, we'll just use off-the-shelf things, except that, well, every company had their own issues. There were supply chain issues, workforce issues, and all that comes together into this very complex situation. So difficult, challenging engineering environment, difficult, challenging mission, and then the pandemic, over all of that. But what we ended up with is this as the rover. This is the Viper rover. It's a fundamentally electrically powered rover. There's solar arrays on 3 sides and a main central battery that's used for energy storage. It has a total of 8 cameras for operations. There's a navigation pair on the mast, pan tilt controlled. There's a high gain antenna that's for direct to Earth communications. It uses a number of sensors, cameras, a star tracker, inertial measurement unit, and odometry for overall position estimation for localization. And as I said, it carries 3 spectrometers and a 1-meter drill. These cameras are really useful for a number of things. Obviously, we care about it for navigation purposes and understanding its position, but also for using the cameras to understand the interaction of the vehicle with its surroundings. In particular, where are the wheels relative to obstacles in the terrain. This is the flight rover itself. We finished the complete assembly last June, at the beginning of June. This is at NASA Johnson. So this mission here is a mission that was led by NASA Ames, or I should say is led by NASA Ames, but really involves NASA Ames, NASA Johnson, NASA Kennedy, and a little bit of work at NASA Glenn in Cleveland. But here's the flight vehicle. You can see the rover itself on the right-hand side. It's currently lifted above the rover release mechanism, which is the interface between a rover and the lander, which would carry it to the moon and then down to the surface. It's a vehicle that we finished assembly, like I said, literally just before NASA hit pause on the overall mission, but we've continued to do work since that time because, as I said, NASA is looking at taking this mission from being a pure NASA science mission to a more interesting public-private partnership-based mission. And so over the past several months, we've basically taken the flight vehicle and put it through the final set of environmental testing, which includes taking this and putting it in a thermal vacuum chamber to test it, in vacuum at low temperatures. We've gone through radiation testing, shock and vibration testing, all the usual things you do just before you're ready to say, yes, ready to fly. In comparison to some of the previous planetary rovers, you can see Viper is certainly significantly smaller than the 2 rovers that are functional on Mars, Curiosity and Perseverance. It is bigger than the original U2 that China launched. It's about a 1.5 by 1.5 meter footprint. From the bottom of the wheels to the top of the mast, it's about 2 meters. It's this is slightly out of date here. The overall total mass of the vehicle is about 500 kilograms. and its top speed is a blazing 20 centimeters per second, which of course, compared to anything here on Earth seems incredibly slow. But I'll point out that's about 5 times faster than the rovers on Mars. So it is actually a pretty peppy planetary rover, just not really fast compared to anything here on Earth. We designed this, as I mentioned earlier, for the dynamic lunar environment. One of the interesting things here is that dynamic is all relative. As I said, the lunar environment has moving sunlight illumination, solar illumination, and moving shadows. In various places that we've targeted for Viper, those shadows move at about 1 centimeter per second, which is also about the average speed that Viper is designed to accomplish. It can drive at 20 centimeters per second, but it doesn't drive continuously. Average target speed is about 1 centimeter per second. So you think about shadows moving 1 centimeter per second, vehicle moving 1 centimeter per second. That means you've got to be very careful about where you're actually going to send the robot. And so there's a really interesting set of constraints that go into planning for how you do mission operations. We did try to design this to be more interactive with the ground. And so even though it is designed to operate very similarly to Mars rovers, that is, we send it a command and then the vehicle carries it out. We don't joystick it in real time. It's not like driving an RC car. It is significantly higher operational cadence. On Mars, we might actually do this command cycle where you basically send commands to the rover once per day, and the rover executes a long series of commands and then sends you the data back. Instead, we made this more interactive where the command cycle is about 4 minutes. So every 4 minutes, we're sending commands, the vehicle's executing it, sending data back down, and we rinse and repeat over and over and over. Another thing here is that in terms of the overall design of how would you actually operate this vehicle, both in terms of driving and operating the instruments, we took a lot of cues from a variety of places. Obviously, the way we've done space shuttle, robotics operations, space station operation, and Mars rover operations, put those all together in some interesting way, and that's something I'll talk about later on in the talk here. Another thing that's interesting too is that we took this this opportunity to take a look at how could we re-envision the way we design computing and software for planetary rover missions. So this rover has a base computer called a RAD 750. It's a radiation-hard computer, ultra reliable, ultra expensive, and incredibly slow. If any of you have ever, I'm not even sure how many people in this room have ever played with a 1997 Power Mac G3, that's sort of like the main high performance you can get out of this. It's really slow. But then we tried to improve the computing performance on board by adding in a radiation-tolerant processor. Now, it's not modern day. It's still only equivalent to like a 2010 iPhone 4, but still, it's a 1 gigahertz PowerPC processor. Now, the difference, of course, between radiation-hard and radiation-tolerant is that the rad-hard one is basically bulletproof. The radiation-tolerant one means that it might reboot because it might be hit by something, and then basically that will force the system to just restart, but will restart without being permanently damaged. In addition, we took a look at the fact that this is a rover that's being designed to operate on the moon with interactive control from the Earth, and that allowed us to do some really interesting things with software. One of the things we chose to do with software is to basically take all the code that would normally be on board and we split it in half. So some of it runs on board, but the other part runs on the ground. And that allows us to do things that are really interesting. Like we can use commodity desktop computing. We can use your favorite Dell high-performance desktop workstation. And we can use things like ROS. So we actually use ROS2 as part of the overall flight rover software. It just happens to run on the ground and is connected by sending data back and forth from the rover on the moon to ground control on Earth. I mentioned earlier that the rover carries a number of science instruments on here. I'm not going to go into detail here. If any of you are interested in, for example, spectrometers or drilling, I'm happy to point you at people who work on these areas. But I want to point out that these instruments were chosen to really support a prospecting mission. We use a near IR spectrometer and a neutron spectrometer as the primary ways of measuring the presence of hydrogen on the surface and the near subsurface. We use the 1 meter drill to get down into the subsurface, down to 50 centimeters to a meter, pull material up, and then we analyze the composition using a mass spectrometer. But now let's get into more interesting things for those of you in the room or online who are roboticists. I want to spend a bit of time talking about the mobility architecture because I think it's a really interesting thing that we've done for Viper. Viper has a total of 12 degrees of freedom for its ability to move. It has 4 independent wheel modules, each of which have 3 degrees of freedom. So there is a suspension joint that controls basically the position of the wheel relative to the terrain. There's independent steering and independent propulsion, that is rotary driving actuation. The wheels themselves are 50 centimeter diameter wheels. They are 20 centimeter wides. They have grousers on there to improve our ability to grip onto the surface and to climb rocks in particular. And what's interesting is that we use all these degrees of freedom in a number of ways. There's a sort of nominal operations where we are just driving with sort of explicit steer driving, but we can also use coordinated control between the propulsion, the steering, and the suspension to do interesting things as we move across the terrain. To test this, we built what we term a mass equivalent prototype. One of the challenges of doing development of a planetary rover for the moon is how do you test this here on Earth, when the moon has 1/6 the gravity that we have here, and yet we want to be able to assess, for example, the driving performance. Now, for some systems, the way you do that is you create a gravity offset system. Small scale rovers might be actually offset by putting actually literally a balloon and lifting up. If you've ever seen the movie, Up, that's kind of what you do to test small rovers. Now, you can't really do that with a larger rover like Viper, and so the best approach that we've been able to come up with is to reduce the mass to create a basically engineering model that is 1/6 the mass of the flight vehicle, and then therefore we can have at least similar kinematic effects. And because of the slow speed system, we're not really worried about all the sort of inertial higher speed dynamics here. And so we created this mass equivalent prototype. We've done testing with it. This is just demonstrating here the different degrees of freedom here. So you can see drive and you can see steer. I think it's going to show suspension as well. This allows us to, obviously to have a lot of flexibility in how we control the vehicle, not just in terms of the way it drives, but we can take advantage of these extra degrees of freedom to do things interesting with the chassis. So we can maintain, for example, the chassis level as we're going up and down slopes or over obstacles. We can raise or lower the bottom of the chassis from the train to get us greater, ability to spread the wheels out or to turn in certain circumstances. We've done a lot of work in terms of development of the mobility system because obviously the primary purpose of a planetary rover is to be mobile, to carry instruments to various locations. Part of that has to do with, how do you go about testing the wheels? It's a really sort of basic fundamental thing, will your wheels survive the duration of the mission? And of course, for a mission like Viper going to the moon, we're encountering rocks, worried about slopes, and we're worried about the sort of high friction soil that we see on the moon. So we spent a bit of time coming up with a test rig. This is actually work that was carried out by Proto Innovations, Pittsburgh. They had the wonderful experience of trying to drive a rover wheel back and forth 40 kilometers inside a small, like 3-meter test chamber. So you imagine this takes a lot of time going back and forth and just trying to assess the failure mode and the degradation over time. But it's a really fundamental thing that you need to do. We've also did a lot of testing at an interesting facility at NASA Glenn in Cleveland called the Slope Lab. You can probably guess why it's called the Slope Lab. It's a place where we have a lot of lunar surface soil simulant. So this is not actually lunar soil, but it's a material that's designed to be as similar as possible from a terramechanical point of view to the soils on the moon. And they have the ability to put this on this large incline adjustable test bed so you can raise and lower this to simulate different slopes to drive on. And of course, with this material, you can do other things too. You can create your own set of craters by hand. You can put rocks on by hand. And then you can test the combination of slope and material and positive and negative obstacles as you're driving over that, while using, for example, external position trackers to get ground truth information of how the vehicle moves. One of the things we did early on was try to look at rock traversal. So this is our smart rock. It's basically a rock with a load cell attached to it because we're trying to understand as you're driving across that, what are the forces that are applied. Of course, what we care about is not really necessarily are we going to damage a rock, but we are interested in understanding how well can we sense the applied forces. Because one of the things we do with suspension is to adjust the amount of pressure that each wheel applies to the surface to try to even out the overall sort of like weight load on the surface. Done a lot of interesting work to basically try to torture test robots. So for example, one of the difficult things to do is to traverse a crater that's the same scale as the footprint of the vehicle. So here you see about a 1.25, I think, meter crater. The vehicle has a 1.5 by 1.5 meter footprint, trying to look at, can you get stuck in that? This gives you an idea. This is at 4 times speed of what happens. Obviously, this is a very soft material. So one of the things beyond just will you get stuck because of the geometry is, are you going to basically do a lot of significant excavation and basically dig yourself in? That was actually one of the big concerns because going into these permanently shallow regions, there's not a lot we know about the overall surface composition. We don't know how soft, how porous the material is in these areas. The lunar scientists, as part of the Viper team, have characterized the material as being fluffy. Now, I mean, fluffy is a great description if you're saying, oh, yeah, well, it's kind of fluffy. It's horrible if you are a mechanical engineer and want to understand how to design vehicle driving performance. You can't use fluffy as an engineering term. And so we did a variety of testing to try to convince ourselves the vehicle could deal with even fluffy soil, especially on slopes. So a lot of extreme slope testing, looking at slip and embedding and entrapment. We've also created a real-time onboard slip detection that uses a combination of encoders, motor current, and IMU measurements here to assess the amount of slip as we're driving over, for example, rocks and into craters. This is actually used as part of the overall control system here to basically stop the rover as it's starting to dig in as a way to try to prevent getting to into an entrapped situation. And we've also done sort of really difficult soil driving. One of the things that NASA Glenn that they have is this tank that they refer to as the sink tank. So this particular tank is not filled with lunar simulant soils, but instead is filled with phyllite. So very small ceramic beads. It's probably the most difficult thing you could ever drive a wheeled vehicle in. Most of the time you put wheeled vehicles in this tank and they really sink, they get stuck. We found that we were able to make progress in various ways, but it was a key part of our testing, sort of like the worst of worst cases that you could think about. And you can see that it's very easy in this kind of sink tank to get really buried. A half a wheel diameter is like the worst case for a wheeled vehicle, because at that point, you're basically just excavating and circulating the material around and not really making progress. But we also designed and tested these alternate mobility modes, which use these coordinated control methods. So here we're using, for example, suspension and driving to do this inchworming behavior. Not your typical design driving mode, because of course this puts a lot more force and stress on the components, but it does give you the ability to move in a very different way to get out of a difficult situation. We also came up with a lot of other kinds of gates. This one is a wheel walking gate. So this is not meant to be a walking robot. It's a wheeled robot. But because we control suspension and steering and drive, we're able to actually walk. And we've tested, lots of different ones. It was kind of fascinating from an engineering point of view of just like, oh, well, let's create something that's an inchworm. Oh, we'll do a crabbing gate. Oh, we'll do a crab worm. We'll do something that looks like a butterfly stroke or a breaststroke. All kinds of different opportunities here. And I think, for me as a roboticist, it's really fascinating just looking at what's possible when you add some extra degrees of freedom, which typically is the thing that NASA, to be honest, will avoid. Because generally what you're trying to do is basically design the minimally viable system. But in this particular case, because there's so much uncertainty about the terrain conditions, we were given the ability to basically be a bit more creative and to try to build in more capability of how we can drive. And I think this is a really interesting thing to do with wheeled vehicles. The idea that you can do these kind of hybrid rolling, walking gates, I think is incredibly important for future missions. Now, one of the things that you might wonder is if you get to the moon on a lander, how do you get off? And there are a lot of different approaches that people have been talking about from various lander companies. The most common, of course, for a vehicle the size of Viper would be to use ramps. Now, even though you might look at a ramp like this, it may only be like 4 to 5 meters, and you think, oh, well, that's trivial. You're only driving 4 or 5 meters. How hard could that be? Well, the problem is this is like the most critical thing you will do once you land, because if you screw up getting off the lander, then that's end of mission. And so for us, it was important for us to do a lot of testing of how would we actually egress in some very safe, controlled manner where we're trying to minimize overall risk. So we did a fair amount of egress testing here in a variety of conditions. One of the things is that if you have a wheeled vehicle going down ramps, of course, the ramps could be splayed. They could have a variety of twists associated with that. They could be uneven at the bottom. And of course, it's interesting that you have a vehicle with the ability to control suspension, which means that maybe you can tolerate a lot of these sort of abnormal conditions. And we did a lot of testing to convince ourselves that that is in fact true. Another interesting thing is being able to point while moving. Viper is designed to be a system where, because we split the software and because it's meant to be interactive with the ground, we're always communicating with the Earth as we are on the surface, including when we're driving over rocks and up and down different slopes. And so the question is, can you, for example, point the antenna at all times, even as you're going over rough terrain? This is an outdoor test, and I'm not sure the video will play here, but we did this at nighttime where we sort of inverted the problem. Instead of trying to pretend we're on the moon tracking the Earth, we thought, well, we'll be on the Earth, we'll track the moon instead. And so we placed the camera at the place where the antenna would be, the high gain antenna. And as we drove, we tried to acquire continuous pictures of the moon while the moon remained centered in the field of view of the camera system. I guess it's not going to play, but we also did a lot of camera testing and light testing. Viper is designed to be the first vehicle, the first planetary rover ever with headlights, basically. Because it is going to these really dark regions. And of course, what that means, you have to do a lot of testing. This is an outdoor test bed at NASA Ames. It's actually in daylight, incredibly benign looking. I mean, it'd be like walking over the most calm beach you can imagine. But at nighttime with these long cast shadows, especially in places where you have sharp relief, like at the edge of sharp craters, it can look incredibly hazardous. And so I think one of the interesting things here is the question of, from a perception point of view, whether it's human perception or machine perception, how do you understand what's really there versus what may appear to be incredibly dangerous or difficult? So to answer that question, one of the things we also did was to develop a laboratory with the incredibly creative name of Lunar Lab at NASA Ames. This is a high fidelity appearance-based test bed. And Cindy here at least has had the pleasure of testing some of her robots there. But it's a place where we have 12 tons of Lunar Highland simulant number 1. It's designed to be a high fidelity appearance simulant. That is, it looks a lot like the material we expect to see on the moon in terms of its albedo, its reflectance properties, and done a lot of testing in this terrain of cameras on board the system and the use of lights. Hello. Yeah, so this is the test bed. The main test bed is a 4 by 19 meter sandbox, again, with about 12 tons of the simulant here. We painstakingly, by hand, constructed craters. When I say we, I should really admit, interns created craters and rocks. So if you come to NASA, you'll be put to work making lunar terrains as part of of course, the testing here. And we use this facility, as I said, to really understand the performance of, for example, computer vision systems based on the data that we can acquire in a testbed like this. I mentioned earlier that we've took some liberties to take the flight software and not have it all reside on board. But the portion that does reside on board is based around what NASA has been using for a number of different missions for several years, called the Core Flight System. It's an open source flight software stack. It has sort of like the base sort of foundational components that you need for any spacecraft. That is, telemetry processing, command processing, memory management, memory scrubbing, that kind of things. And then we build up on top of that all kinds of the custom apps that you need for a robotics mission. The overall development here, something that took over the past, 6, 7 years, a team of 25 engineers working just on software. So there's a lot of code here. There's a lot of automated tests that we had here, over 8,000 automated tests that we've developed here. It was deployed to run under VxWorks and Linux, both on, as I said, a rad hard computer and a rad tolerant computer. So lots of work in terms of developing that. We also did create, and we're very happy about this, ROS2 based code. That's the portion that we chose to run on the ground. Most of that is focused on navigation. So that's where we do a lot of the computer vision work for position estimation, for hazard assessment. It's implemented as a set of ROS2 nodes. We do a lot of work in visual odometry and then 3D to 3D train matching. And then there's a pose corrector, which basically maintains a large factor graph that we use to continually update the overall pose estimate as we're moving. Now, I only have like 15, 20 minutes left, and I want to make sure I have time to answer questions. So we'll just try to zoom through the last bit here, which is about mission operations. And that starts off with mission planning. Viper, as I said, is a mission going to a challenging dynamic environment. And because of the short duration mission, that means you have to be very efficient with the use of time. And so planning in terms of like traverse plans and activities is a very important thing. With Viper, we use a lot of automated methods for this. Some of these are classical scheduling methods. Some of these are classical, constraint-based solving methods to come up with plans that it might be focused on activities or resource utilization or traverse. But they have to take into consideration lots of factors, such as the distribution and state of the volatiles that we've discovered. The fact that it's a solar-powered rover that has limited battery, which means limited ability to tolerate being in shadow. The fact that you have to do with line of sight communications, you have to reason geometrically about, can you see the Earth from wherever the rover might be? The design limit of the drive system, the speeds that you can drive at, moving shadows, all these various factors. And we ended up with an overall planning process that makes use of high resolution digital terrain models, feeding into some strategic planning, as I said, really constraint-based and POMDP solvers for the strategic planning, and then timelining to come up with the sort of detailed tactical plans. At the end of that, you end up with this kind of thing. This is a dynamic traverse. This is an example of if we had flown in 2023, one thing we could have done would be, if you see the arrow, that's representing where the location of the rover would be over time. And sometimes it goes to locations and it basically pauses because you're waiting, like right here, it's waiting for the sun and shadows to move around in the right configuration so that it can then proceed. There are also the cases that you might have to go to these locations where you have short duration lunar nights and have to stay there for some period of time. Again, really interesting planning problem. If you're a planning person and want to know more details, I'd be very happy to point you to a couple of people on the planning team. Just wonderfully challenging planning problem. Another thing, of course, that goes into mission operations is how do you basically develop and test the way you're going to do operations. And so one part of that is that you need a high fidelity simulator in order to be able to recreate the lunar conditions and then use that as part of the overall way that you construct the training curricula and basically the practice that mission operations people do. I mean, when you fly a mission, you don't just say, okay, hey, now that we're there, how do we operate it? But instead, you spend an equal amount of time designing mission operations and practicing that before the vehicle's even finished, so that when you're launched, you're actually ready to carry out mission operations. So to do this, we developed a high-fidelity real-time simulator. It supported mission design as well, so we use this as part of overall software engineering as part of our test suite. But then we use this to really test out different sort of operational constructs, one of which is the team or the sub-team that controls the rover. How do we do this in a very interactive way, very different from, say, past rover missions? To do that, we built a simulator, has the name of RSIM, which stands for Rover Simulator. Sometimes we're not really that creative. But it's a simulator that has high quality lunar lighting, high fidelity camera models, a lot of detailed modeling of the camera systems, real-time slip modeling, and takes advantage of high resolution real terrains and then very high resolution synthetic terrains that we created. And I want to point out that this entire system is built on top of Gazebo, or at least Gazebo Classic. And it's something that we are actually planning to open source as soon as we have a moment in time to actually do that. As I said, we incorporate very high fidelity camera models because we want this to be accurate in terms of what kind of data our computer vision algorithms see and what the operators see. So we've done a lot of work in terms of actually testing in the Lunar Lab engineering cameras and using that to tune the simulation in terms of things like exposure or lens flare, fixed pattern noise, flat field effects, depth of field. So really high fidelity camera modeling, because that's really critical to a lot of mission operations. We've also developed a lot of these high resolution terrain models, these digital elevation models of the moon. Part of my group at NASA Ames for a long time has been focused on automated stereo photogrammetry. And we have a software suite called the Ames Stereo Pipeline. It's open source. It runs under Linux and Mac OS. And we use that to create these high resolution maps of data based on, for example, camera and laser altimetry from the Lunar Reconnaissance Orbiter. So you can end up with, for example, DEMs that are on the 3 to 5 meter per pixel scale. But over the past few years, we've actually applied photoclinometry techniques and basically processed many, many images, so dozens of images showing shadows across the same patch of terrain, and use that to reconstruct higher resolution, so 1 meter per pixel DEMs. So these are the highest resolution 3D terrain models that exist to date for the moon based on satellite imagery. But of course, a 1 meter per pixel DEM is great for high-level science planning. It's not really sufficient for rover scale planning when you especially have wheels that are only 50 centimeters. And so you care about, like, say, a 20 centimeter rock. So what we've done in addition to that is develop a set of tools to create synthetic high-resolution terrains that start off with actual 3D terrain models, such as the 1 meter per pixel DEMs. And then we create scientifically plausible higher resolution versions of that by applying the size frequency distribution models we have of rocks and craters to the surface. And so, for example, we'll start off with this. This is a typical 1 meter per pixel DEM. That's the output of the Ames stereo pipeline. And then we'll end up with a 4 centimeter pixel synthetic DEM here, which we use for simulation purposes. When you put that all together, this is what you see in Gazebo. This is just a snapshot of basically flying down towards a rover here. You can see here the appearance of the lunar surface. And this actually has matched pretty well some of the images that we've seen in the past week or so coming back from the landers that have been on the moon near the lunar South Pole. So we're very happy about that at a qualitative level. But again, this is really driven by some detailed studies of the rocks and craters and the slopes in the area that we expect to operate. And the lighting model is something that we spent a lot of time testing both in the lab as well in simulation. In terms of mission operations, the way that we've designed this here is that it's a mission that would be operated in real time from NASA Ames in California, where we basically drive between science stations. Going from a science station to science station is basically get there as rapidly as possible, as safely as possible. And in the science station, you might do things such as these kind of lawnmower pattern systematic surveys to acquire measurements. Now, a science station might be focused on a permanently shadowed region or an area we expect to see certain types of volatiles at certain times. And then all this is the output of the overall planning process. From an operations point of view, I mentioned earlier that Viper has tried to draw a lot of inspiration from prior different kinds of robotic missions in space, especially Mars rovers and the space station robotics. Now, of course, Viper is a bit of a different kind of mission because it's on the moon. It's not in orbit. So it is an unstructured environment, which is more similar to Mars, but the science is different, and obviously the surface conditions are very different of Mars. And because of that, we've ended up in this space here where Viper focuses on real-time interaction, these kind of like 4.5 minute command cycles with a lot of interaction between the ground control team and the vehicle. And on the ground control side, a lot of interaction between the operational team and the science team. This is a snapshot of the NASA Ames Mission Control Center here. What you see here is the real-time operations team. So in the back row, we have the flight director, people who manage systems and commanding to the vehicle in terms of sending scripts for automating control of various subsystems like communications and power management. But in the front row is the drive team. These are the people responsible for the actual operation of the rover, at least in terms of commanding for where the rover goes and the use of its camera systems. And that consists of a driver in the center who has primary command authority, a real-time scientist who assists the driver in terms of especially terrain hazard assessment, a co-driver that helps with sort of near-term tactical planning and confirmation sanity checking, and a navigator who's responsible for monitoring overall position estimation as you're driving. This is a structure that we started out testing back in 2023. We've done a lot of work in terms of trying to optimize the command cycle to make that as efficient as possible, because as you can imagine, it's a pretty high workload task here, even with automated decision support tools, even though that a lot of things like navigation is handled automatically, like through ROS, for example. There's still the whole question of, how do you assess the terrain that the computer vision algorithms are giving you? How do you make decisions about where to actually go, which might be based on not just what's safe for the rover, but what's required for science measurements? And how do you do this in real time? And And so the overall approach for driving Viper was one based on the idea that we would use these command cycles. We would send position-based commands, so waypoint commands, that would command the vehicle every 4 minutes to move between 4 and 8 meters from its current location. And then allow the rover to achieve the onboard motion control and positioning to go from point A to point B. But along the way, a lot of interesting things you have to take into consideration, various driving techniques, such as, are you driving down sun or up sun? And what does that do to the ability you have to actually acquire appropriate camera images? Sometimes it's the case where the best view of where you're going to be is from where you were previously, not right when you get there. And so there's all this sort of view planning that has to go on as well in terms of trying to optimize when you collect imagery and when you don't. This is the rover driving interface, at least the main tool. There are a number of different tools that we use for mission operations. This is the primary one. It's a 3D graphical user interface where the center we see display of 3D terrain models, both a priori built from satellite data and real time that comes from the vehicle. You can also see overlaid on that a hazard map. That's the assessment from our ground processing, where we basically take stereo images, convert those to point clouds, and then apply a variety of metrics to assess hazards in terms of slope, step obstacles, positive and negative, that the vehicle can handle, and then turn that into a color-coded representation of the level of hazard that the terrain poses to the vehicle, at least from a geometric standpoint, to the vehicle. And of course, a variety of other controls for commanding various different motions and the use of cameras. So the way this works interactively is that the operator, the driver, will place a waypoint. You can see this circular puck and the representation of the rover. Of course, the rover has limited steering authority, and in fact of how far it can turn based on the range of motion of the steer angles. And so you can place the waypoint in the 3D terrain, where is the merger of the hazard map and the local digital elevation model that we have of the area. And then what you see actually on the inset here is the rover simulator, the RSim, that represents what the rover would look like on the moon. If you were on the moon, that's what you would see. But here, I'm just showing as an inset here. And then after you've placed the waypoint, you might look at, for example, prior imagery to go do additional assessment to confirm that, yeah, the computer vision algorithms weren't wrong. And in fact, that we do actually see what the terrain looks like. And then, if you're satisfied with all that, you'll command the vehicle to move. And because it's interactive with the ground, because it's only a few seconds in terms of round trip communications, and we're going to do another waypoint in like the next 4 minutes, as the vehicle is moving, you can go on and actually start pre-planning the next location and do this over and over and over again. So very interactive, not real-time joystick and control, but still allows our ability to have humans take a look and basically sanity check the output of computer vision algorithms. And so it's not a fully autonomous rover. It is not a fully manual controlled rover. It's someplace in between. With that, I think I'll wrap up here so we have time for at least a few questions before we kick out of the room. Viper, is this really fascinating mission that we've designed over the past several years, designed to go really explore the lunar terrain and assess the distribution of subsurface volatiles. It's something that I think is fascinating as like the first surface prospecting mission to ground truth everything we've learned from orbit and to help open up the future towards the use of these resources for scientific purposes and exploration purposes. So, I do expect to see Viper flying. Definitely not this year, maybe next year, or maybe in early 2027. So stay tuned. I'm sure I will come back at that point and give you sort of like, hey, pictures from the mission, not just as designed. But with that, I'll stop here. If anybody's got questions, I know we have a few minutes, and I apologize for being a little bit late earlier.
So I'll start with that was a really fascinating talk. Maybe just a kind of a commercial question. Interesting thinking about both having industry participate in the launch as well as thinking about future commercial potential for the moon. The data that's found, like where the water is, how much, all that kind of stuff, that seems like it could be super valuable from a industry perspective. Do you have, what are the policies going to be in terms of making it public or?
Yeah, so because NASA decided to go down this path of trying to find a commercial, public-private partnership thing, that question is an incredibly important one. Because as you said, a lot of industrial commercial interest in the moon is focused on resources, and obviously having surface level ground truth could be incredibly valuable. I will say that's an area that is still under active debate because in the past, all NASA science missions, released the data because it's public information. It was paid for by U.S. taxpayers. Although there typically is like a sort of period of time where the data is held and reserved because the science team associated with it obviously is going to do analysis and write papers, and so it's not released immediately. I imagine something like that might happen. There's also questions of if there's going to be derived data from the analysis. Maybe that's something that is done on the commercial side, and so they get first crack at it, and so maybe it's like time to market could be of interest too. I don't know. It's an unprecedented opportunity for creative lawyers, I think. Oh.
Thank you for the wonderful talk. I noticed that most of the previous rover has 6 wheels, and Viper suddenly has gone down to 4. Is there a reason why this decision was made? And is there a reason why not making the wheel a little bit larger so that it won't trip?
Yeah, so the first part, why 4 wheels versus 6? All the past rovers to Mars have used a 6-wheel rocker bogie passive suspension design. For Viper, when we were going through the system engineering work, we decided that we wanted to add the ability to have adjustable suspension, number one. And so the question is, if you're going to do this in an active way, should you use 4 or 6 wheels? But then you throw in other constraints, the fact that this has to be a solar-powered rover, which means that the solar arrays have to be mounted fairly vertically, and you want to try to maintain maximum illumination to the sun. Those factors led us to ultimately say, well, we'd like to have at least 12 degrees of freedom. And of course, one of the big things that you then worry about for any sort of spacecraft design is how do you minimize mass? So if you can get away with only using 4 wheels and not a bogie on there, maybe there's some mass savings. And that's why we ended up with 4 wheels versus 6. Also, because we have this extra ability to control suspension, we felt that the trade-off of giving up sort of stability that you get from the 6-wheel rocker bogie was more than made up for by the adjustable active suspension system. Now, we don't yet know if that truly will work out. And we've done a lot of testing here on the ground, but of course, it's limited. The real proof will be, can we actually operate successfully on the moon and not get stuck? And if we get stuck, then the main mobility designer will say, okay, maybe we should have used the 6 wheels.
Hi, thank you for the great talk. I have 2 questions. First one is similar to Professor Seem's question. So about the commercial side, you mentioned you considering the commercial partnership, right? So is it only about like commercial launch provider, but or also about sharing the data with private companies? And if it's about also sharing the data, do you also consider if it's a private company that will tell you, we're really interested in that mission, but we would also like to have this data. Are you also considering adding additional sensors to the rover to like make both parties happier? And,
yeah.
Yeah.
So let me just sorry to interrupt here, but I mean, one of the things that the NASA struggled with over the past few months in trying to figure out how to basically announce an opportunity for partnership is, what are the constraints that NASA would apply to industry? And one of the things that we were trying to avoid was, further delaying the mission, which, means that if you add anything, if you make modifications, whether it's hardware or software, obviously that will cause you to do more engineering and more testing and more verification of that. And so at this moment, we're trying to move down a path where there are no modifications to the hardware, and maybe modifications to software are as limited as possible. Now, having said that, obviously, there's still a lot of interest in terms of, well, given that we do have a variety of sensors on board and a variety of instruments, maybe there are particular measurements that a commercial partner would want to do that we had not planned for from a purely scientific point of view. So those are definitely within scope. The idea that you could say, well, we actually want to get more of this kind of measurement, which NASA had not really focused on from a science point of view. So that might happen.
All right, thank you. Just one more question.
Yeah.
I really like your idea about having the slower computer with really high TRL on the board and then like more expensive computation on the ground. is latency any issue at all? Or like because the rover is not moving that fast that you can like accommodate for that? Thank you.
Yeah, and the rover doesn't move that fast because it spends most of its time sitting still. We have started looking at just the fundamental question of how fast could Viper move if we didn't have, this pesky human review decision time? Could we drive continuously, and what does that actually involve? I certainly think that the computing choice is driven primarily by our decision to look at certain things that have to be computed on board. At the moment, because we have things on the ground, we do take the latency hit of having to downlink certain kinds of information. So for example, we don't send down full high resolution uncompressed imagery. We do some onboard pre-processing of images and try to send reduced images down to Earth for processing for computer vision point of purposes. And so I think it's this combination trade between how much computing do you have on board, what you're trying to do on board, how much you're willing to basically off-board, by downlinking information from the moon to the ground, and what you can do on the ground. In many respects, it's the same kind of trade-offs that we see for all the sort of like cloud-based computing that people do, whether it's with apps on your cell phone, or there was a big push a few years ago for sort of cloud robotics, the idea that, well, we don't need a really stupid, simple brain on board, and everything's going to be done on the cloud as long as we have communications. And of course, the problem there is as long as we have communications. Yes.
Thank you so much for your really interesting talk. I also have two quick questions.
Okay.
I was wondering if you had any sensors on the rover that picks up forces experienced from the ground.
Yeah, so the first part is we have load cells that we use for sensing, especially like downforce from the wheels. We also make use of motor currents. Obviously, I mentioned we do slip estimation, real-time slip estimation, which has not been done before on planetary rovers, and that also takes advantage of the load cells plus the motor current plus the odometry and IMU measurements as well.
So the second part of my question was, you showed us a couple of really interesting locomotion modalities and gates.
Yes.
Is there any work that's looking into what the terrain-robot interaction is like, and what these gates are good for in terms of which kinds of interactions they'll work best in?
Yeah, we've done quite a bit of testing. I know there's at least one paper in preparation that's talked about the assessment we've done. There's obviously, I think, a lot more research to be done in terms of looking at the overall efficiency of the gate. What is the impact in terms of if you design, for example, if you size actuators and like the support structure for certain levels of forces, how does that, lead to limitations of how long or how often you could use those different gates? I think there's a lot more interesting things too about what can you learn from from a thermomechanical point of view from driving in this way. I mean, we already know that we can infer a lot about the terrain just by measuring slip in real time or by looking at wheel tracks. But now if you have the ability to use combination of suspension and drive and steer, maybe you can learn more. And so now the entire vehicle becomes an instrument for just looking at terramechanics.
Thank you so much.
Hi, thank you for a great talk. So my question basically is that if I understood correctly, there's a 4-minute delay between communications from Earth to the rover. So if there's some sort of emergency situation, the rover is kind of stuck somewhere, or it has to perform some computation in those 4 minutes, what are the emergency algorithms that you have that the robot will decide to do in those 4 minutes of delay between communication from Earth? Because I think 4 minutes is a long time.
Yeah, so so first off, the delay is not 4 minutes. I mean, the 4 minutes is just happens the loop time between our ability to send signals. I mean, the round trip communication delay is on the order about like 6 to 10 seconds if you include ground station buffering. So it's near real time. But your question is about onboard autonomy, and the vehicle is designed with autonomy focuses primarily on safeguarding. So obviously, if there's like a timeout in terms of when it's receiving command, the vehicle will stop. I mean, there's continuous basically uplink and downlink sort of heartbeat signals that we use to say, yes, we're in communications. In addition, by far the biggest risk that we are worried about is loss of communications because we split the software, because it's meant to be interactive. And so the vehicle on board has this very detailed, complex sort of fault tree that it works through when it detects it loses comm. So the first thing it will do is it will stop. and then it will try to repoint the antenna based on where the Earth should be. Because of course, we understand the Earth-Moon ephemeris and basically how they are related to each other in space. So in theory, we should always know exactly where to point to see the Earth. After that, you go to things like, oh, we're going to power cycle the transceiver. And I think, second to last step is, okay, we're going to try to move to recover communications. Because maybe we move to some place where there's an obstruction, or maybe there's multipath interference. And so the rover knows when it last had good comm, and will say, okay, I'm going to try to my best of my ability, get back there. Now, of course, there's no guarantee because trying to reverse drive, you can often get into situations where maybe we'll collide with something, maybe we'll slip with something. But all those things go into the general category of basically fault management.
Okay, let's give our speaker another round of applause. Thank you. So next week is spring break. So our next speaker will be Max Schwager from Stanford University. That will be March 28th, 10:30. For more information for upcoming events, check out our website and follow us on social media. Thanks for coming. Yeah.